Hello, my name is Kentaro Barhite, and I'll be presenting our work on a high-strength, highly flexible robotic strap for harnessing, lifting, and transferring humans. Grasping and lifting humans is a challenging task that robots have yet to achieve. Humans are heavy, soft, delicate, and vary widely in shape. Thus, there exists a contradiction between the high lifting forces and gentle interaction necessary for safely grasping and lifting them. Straps, on the other hand, are highly practical for lifting humans and are commonly used in the elder care and patient care industries. Straps can be wrapped around the human in various harnessing configurations to distribute the high load over a large contact area, and thus straps bypass this contradiction. However, straps require manual handling by a caregiver to attach them to the human, which presents a bottleneck in preventing the automation of this task using straps. A robotic strap capable of automating the harnessing process would allow for the automation of this overall task. In prior literature, a few robots have demonstrated lifting the full weight of a human for transport. However, these robots do not address the problem of safely and securely harnessing the human. Alternatively, soft robots can provide compliant and safe interaction with objects because of their soft material construction. However, they cannot bear heavy loads on the scale of a human body. In this work, we present a novel concept for a robotic strap-like manipulator that can articulate itself around the human into the desired harnessing configurations and be actively retracted to safely secure, lift, and suspend them above the ground. We define the robotic strap concept as a manipulator with an actuated strap-like structure that can articulate itself when active and maintain the passive strap-like behavior when idle. The strap-like term indicates that the structure is characterized by the physical properties of passive straps that make them beneficial for harnessing and lifting humans, which are its high tensile strength, which provides its high load capacity, and its high bending flexibility, which we quantify in terms of the structure's passive bending resolution, resistance, and curvature. The robotic term indicates its ability to automatically extend and articulate itself around the body into the desired harnessing configurations. We present a minimal design framework that describes the key fundamental features of the robotic strap design, which consists of a serial chain backbone with rigid links and zero stiffness joints, which provides its highest tensile strength, and soft artificial muscles embedded along the chain to bend the joints, which enables active self-articulation. The combination of these features makes the structure completely backdrivable, buckling resistant, and statically determined as well. This provides its high passive bending flexibility while maintaining its structural integrity when actively articulating. Based on this framework, we developed the full design of the robotic strap, which consists of a hyperarticulated backbone with rolling contact joints held together using a dual pulley fastening mechanism, which provides a lightweight structure that can be pressed against the human body relatively safely, and a series of soft pneumatic thin McKibben muscles embedded along the side, which adds minimal stiffness to the joints. We implemented this design in a prototype that is over a meter long, has 30 joints, 3 active degrees of freedom, and weighs just under half a kilogram. We modeled the key performance metrics of the design in terms of its key parameters and calculated the theoretical results for our prototype. All our results showed promising performance for safe harnessing and lifting of humans. Our experimental characterization of the prototype also showed that its performance was sufficient for harnessing and lifting humans. 2 demonstrations were performed to further illustrate the robotic strap's capability for automatically harnessing, lifting, and transferring humans. The first demonstration shows a robotic strap's capability for harnessing and safely lifting the full weight of a human. Here we can see the robotic strap automatically harnesses the subject, lifts them, lowers them, and disengages the harness configuration. The second demonstration shows the robotic strap's ability to perform a standard task commonly carried out in the elder care industry. In this case, we demonstrate a chair-to-chair transfer. Future work includes improving the performance of the robotic strap through design optimization, miniaturization of the robotic strap for wearable applications, exploring different designs within the robotic strap paradigm for different functionalities, and developing dynamics models for autonomous control.